Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Gauri Joshi. I'm an associate professor at Carnegie Mellon, and I'm co-organizing and co-hosting this semester seminar series with Professor Richard Zhang, who is an assistant professor at the University of Illinois. So before we begin, we would like to pause and acknowledge the support of our academic and industry partners, for which we are deeply grateful. This semester, the seminar series is organized around two special themes. The first is adversarial machine learning, and the second theme is distributed and federated learning. And our talks are alternately scheduled between these two themes every week. So today's talk is related to distributed and federated learning, specifically differential privacy. We're looking forward to hear from Professor Rachel Cummings from Columbia University today. And in the upcoming weeks, we have other interesting talks lined up, as you can see in this calendar shown here. The abstracts for future talks and also the videos for previous talks are all available on the YouTube channel. So we invite you to subscribe to the newsletters and our channel so that you don't miss any of these talks. And if you miss them, you can watch them afterwards. So today we are very happy to welcome Professor Rachel Cummings from Columbia University to share her research titled Improving Communication for Differential Privacy, Insight from Human Behavior. Rachel is an assistant professor in the IEOR department at Columbia and also affiliated with the computer science department and the data science institute. Her primary research interest is data privacy with connections to machine learning, algorithmic economics, optimization statistics, and public policy. She received her PhD from Caltech and her master's from Northwestern and bachelor's from the University of Southern California. She's a recipient of many awards, including the NSF Career Award, the DARPA Young Faculty Award, an Apple Machine Learning Award, JP Morgan Chase Faculty Award, Google Research Fellowship, and many others, which are listed here on the slide. So we are excited to hear from you. Without further ado, let's welcome Rachel. The talk will be 50 minutes long. And for the audience, if you have questions, please use the Q&A feature in Zoom to type in the questions, and we will ask them on your behalf at the end of the talk. So let me stop sharing, and Rachel, you can take over and start the talk when you're ready.
Excellent, thank you. I'm very thrilled being here, and let me try to share screen. Hopefully after many months of COVID, I know how to share screen. It's always a scary part, it works. Wonderful, and you guys can see my screen?
Yes, we can see it.
Excellent. Thank you. So I'm thrilled being here. I guess being the first one of the semester is a great joy. So I'm here talking about some kind of unusual in a good way work with my collaborators, Gabe, Priyanka, Alyssa, Marianne. We all work broadly in computer science space. We come from very different fields, including things like cryptography, HCI, usable security, survey design, data visualization, communication, and of course, privacy. So we're sort of bringing to the table all of our skills, and we're taking a fresh look at the use of a differential privacy. Before I begin my talk, I always like to say that I do have a minor speech impairment, and so if I pause for a little bit during the talk, it's hopefully not just a bad Zoom connection. So, I will start by talking about how might you define a differential privacy to an audience like this, where you assume everyone's some kind of like, technical expert in their own field. How would you explain this like a privacy notion? And I'll give you like a 2 slides of this before we like jump into the actual research. So like a differential privacy was defined back in 2006 by like Dwork, McSherry, Nissim, and Smith. And it goes like this. Imagine if I plug in to my favorite randomized algorithm, I plug in some like a particular database containing data coming from multiple users. And so we plug that in, and because we're talking about a randomized algorithm, I'm going to get out a like PDF of the possible outputs of this algorithm instantiated on this particular database. And so now, like I would like to imagine, what if I change one person's data, say that I change Alice into Javier, and I plug in this new database that is like the same except for one person's data into my same randomized algorithm, well, then I will get out a like slightly different PDF curve of the outputs of this algorithm instantiated on this input. And our privacy guarantee says that we'd like this ratio to be bounded everywhere, like a pointwise across the like domain of this algorithm's outputs. Why is this privacy? Well, so now imagine there was an adversary who observed this like a particular output, and they then tried to infer, was this output produced because of Alice's data or like because of Javier's data? And so we'll know, for example, a Bayesian adversary would not be able to make a very strong influence beyond the amount allowed by this bound. In math, it says this. We'll say that an algorithm M that maps from an n tuple of types, think of this as being like a data coming from n people, into some arbitrary output range R is going to be parameterized epsilon differentially private if it is the case that like for all pairs of neighboring databases that are the same except for one person's data, and for all possible things I may produce as a result of this algorithm, I'm going to output that thing with about the same probability under these two neighboring databases. And you can see that our guarantee here corresponds to like a bounded ratio of these two probabilities. And so effectively, we are bounding the kind of like a maximum amount one person's data can affect the output, but rather than doing it in like absolute sense, we're doing it in a like a probabilistic sense, requiring like a closeness in the distributions. And like now in the past 15 or so years, our computer science community has produced a very diverse algorithmic toolkit for things like differentially private machine learning, optimization, statistics, estimation, you name it, of some tools that will both meet this privacy requirement. It will also enable like an accuracy of the analysis. And these things are now used in practice across a growing like a number of organizations, including the ones listed here and more. But of course, things on my past 2 slides are not how you should explain it to kind of end users. If you want them to really understand privacy guarantees, I probably should not be talking about some worst case Bayesian adversary making inferences. And so instead we have to think about how else can we explain these underlying privacy guarantees without going into complicated mathematics. And our goal of this really is to kind of empower end users to be able to make informed choices about their data. And of course, before they can make informed choices, then we really have to ensure comprehension. And so this will be a talk in 2 parts. And the first part will be about communicating basically what was happening on the past 2 slides. How do I explain fundamentals of the privacy definition? And this is about work that has been published. It appeared in CCS last year. And then a part 2, we'll kind of dive into some of these nuances and things how do you choose as a privacy parameter epsilon, and some other like specifics of the implementation. And that is like an ongoing work. And so I will share more about the state of like that work then. So for our first part, we are really thinking about explaining differential privacy to kind of non-experts. And there, of course, are kind of multiple possible like explanation tools. And we're thinking about something at this scale. There's a billboard. There's a pop-up, and you have space for maybe one sentence, possibly a picture. What do you put on that billboard in a way that kind of like enables users to like really be informed? And by the way, this actually is like describing like a differential privacy. It's not quite what you saw on my last couple of slides. And I have to say, as an expert, it's not also quite correct. It's not that what happens on your iPhone stays on your iPhone, but it is that what happens on your iPhone triggers a random signal that is correlated with your data, and that leaves your iPhone. But of course, that is like a little less like appealing on a billboard. And I want to mention, this is certainly like not the only tool that you might want, but in fact, there exists multiple stakeholders in the path to like deploying DP and to kind of like empowering users. And so you're also going to want to think about how to explain differential privacy to the lawyers, to the executives, to the engineers, to the policymakers, and so on. And I just want to focus and say that we're really thinking about with this slice here, but of course, this is a slice of a much bigger pie. And so our main question is we're thinking about like how does the way in which differential privacy is described impact users' expectations of like a protection against various like information disclosures. And I want to mention in the paper, not today. So we also thought about what a type of like information disclosures users care about, so that we can ask our main question about the like correct information possibilities. And then we also thought about like how does this impact users' willingness to like share data. And I'm happy to like chat about these afterwards, but I won't be covering them in our talk today. So the kind of like a research plan, as well as an outline for this like a portion of the talk, is we first went out in the wild and we collected multiple like privacy descriptions, and these came from both like academic papers, journalism pieces, mostly coming out of like tech focused places, and then also in the like press releases of the organizations using DP. We then conducted like a vignette-based surveys on like Mechanical Turk to kind of elicit people's like privacy expectations based on these existing descriptions, and then we gave them a kind of like a specific information sharing scenario and a specific differential privacy description. And then we asked them about their privacy expectations, and of course, if they would share data. And then we evaluated afterwards how effective each of these privacy descriptions were in terms of like a correctly setting users like a privacy expectations. And so now in this process, as we kind of like went out, we found a whole bunch of kind of like existing privacy definitions. We found things roughly like centered around like 6 themes. And I'll kind of like go through these. And so then like for each of these themes, we created one like a particular kind of like a canonical privacy description that was like a single sentence, and it really captured some of the core ideas of that theme. And our first one is one that was very compelling, but also provided no information. And so it talked about how like differential privacy is a gold standard and it's widely recognized, strongest privacy guarantee available, but it doesn't really tell you anything about what it is, how it works, what it does, and why. Another one focused on the algorithmic techniques that are used to like achieve privacy, including like injecting statistical noise into the data, and therefore like protecting privacy without really changing the results. Our third one focused on the like type of analysis enabled through this process. And so this talked about like allowing analysts to kind of learn information about the population without compromising individual privacy. Number 4 relied like on the trust models, and this included the fact that like major organizations use it and you should trust them. We also found math was a trust source, and so this also included focusing on the fact that it was a formal like a mathematical tool. Number 5 talked about the reduction in risk to the user as a result of this. And so this included protecting a user's identity and their data, and the fact that also this means individuals incur close to no additional risk if they share data. Number 6 was a bit of an oddball in this context, but it was a quote that was taken directly from the academic papers on the topic, in part because we thought this is how things are kind of explained to the experts, and we expected this would not be particularly comprehensible to a non-expert, but also this does kind of capture all the important things, including that it protects individual database records, not affecting outcome of the analysis, no additional risk, mathematical rigor, and so on. And so we included this as a way to kind of evaluate whether the ways that a differential privacy are kind of talked about within the academic communities can be used beyond that. And so given these, then we gave people a couple different vignettes. And so this first one was about sharing salary information. And so we told people, imagine that you work in a banking industry and you're friends with a group of other people who work in banking companies in your city. One of your friends is a part of a transparency initiative that is trying to publish general statistics about pay in the banking industry. As a part of this initiative, they have asked everyone in the group to share their salaries and job titles using an online web form. And then we have this part at the end saying that to kind of reduce the intrusion into personal privacy, your friend says they will use differential privacy. And then we inserted one of our 6 different differential privacy descriptions on the previous slides. And then we also included a no privacy baseline where this last paragraph was gone. And this is to kind of evaluate how do people feel without kind of any mention of privacy protections. And we also had a variant of this that was kind of as close as possible, except to ask about sharing your medical record with a non-private for the sake of improving medical research. And importantly, both of these are kind of positive spins. And so we're trying to make sure there's a reason you want to share data for some collective good, improve transparency, medical research. But of course, you might naturally have some privacy concerns in that process. And so afterwards, as a part of our survey, where we also asked them about some of their demographics and their internet literacy skills and about data sharing. So we also asked them, which of the following information disclosures would you expect to be possible for your data? And we gave them 6 possibilities, and these are the ones that we had previously found in our first survey, looking at the type of information disclosures that are important to the users, and there were these 6. And so a hack includes a hacking by a criminal or by a foreign organization, Law enforcement includes, of course, law enforcement with a warrant or with a court order. Organization is a group that is like collecting data. And so in these cases, in the first one, it will be the a transparency initiative. And the second one, it will be the medical research group. Data analyst is specifically a kind of data analyst working at the organization. Graphs include graphs, charts, statistics computed on the data. And then finally, sharing includes a third-party sharing. So with this, then we can finally ask, how do these privacy descriptions impact users' expectations? And we found things were in fact very, very heterogeneous. There was not a one single method that kind of worked all the time universally, but rather we found that different explanations of DP improve privacy expectations against different disclosures. And we also found these were different across individuals as well. So this tells us maybe you want to do personalized privacy descriptions, but then that kind of opens a whole new can of worms because you're trying to do privacy and then you have to collect everyone's data first. So that's a problem. But I'll first tell you about our findings in a more concrete way. So this chart shows the kind of impact of kind of each of these descriptions against kind of each of these possibilities. And so here, on each row, we have a single privacy description. And so these are R6. And then each column corresponds to a particular privacy possibility, a particular information disclosure. And so having a colored cell means that there is a significant at the 5% level, a change in people's privacy expectations compared against a no privacy baseline. And so, for example, in this first square here, we see that giving people a kind of unsubstantial privacy guarantee, differential privacy is a gold standard, no additional information, increases their privacy expectations against hacks and against graphs, but there was not really an important a difference in the others. And so kind of in reading this, first of all, you can really observe this kind of heterogeneity. And we also see there's some that kind of lead to stronger privacy expectations. For example, talking about the reduction of risk actually does cause users to have stronger privacy protection expectations. Also talking about how it is achieved algorithmically is pretty helpful. Some things are not very impactful. For example, talking about trust of organizations are math, and then this kind of no real content description. But again, importantly, we don't really see one single privacy description that kind of makes everybody feel good against all things. And so we could possibly delve into that, but actually what's perhaps more important here is that we're not just trying to make them have kind of a stronger privacy expectations, but in fact, we actually want them to have correct privacy expectations. And so before we can talk about kind of a correctness to their privacy expectations, we have to talk about two different versions of this differential privacy model. And so there's two different versions, and they are called central and local. And the central model is one in which there exists a kind of single a trusted party who is going to collect everyone's data, store it, analyze it, and then when they publish things to be read by the outside world, they're going to do so using differential privacy mechanisms. And so this is, for example, what you expect if you're talking about the Census Bureau, how there's a government agency and you are and you are like a constitutionally mandated to like share your data with them. On the other hand, we have what's called like a local model. And so this is a case where the users do not trust one single central curator. And so they're going to add noise locally like themselves, like on device before they share data. And this is nice because it kind of like doesn't really require trust. You can think about how this is combined with other tools, including like MPC, but that's a different talk. And so for example, this is what is commonly done at places like Google, Apple, and so on, where they're trying to give you privacy like on your device level without having to share your real data. And so now, of course, if we compare these two, local model is very nice because it doesn't require trust and it gives users stronger privacy guarantees. However, on the other hand, when you're considering accuracy of the analysis, central model is going to add much less noise for privacy, and therefore is going to be much more accurate in terms of analysis. And this kind of happens because kind of in the local model, users are going to add noise on their own, and you'll have this across every user. And so you're going to have a very large amounts of noise in the analysis, whereas kind of on the other hand, under the central model, users are going to share raw data, and the analyst can then just add a very small amount of noise. But of course, as we move into our possibility of kind of information disclosures, we're going to see in the central model, there exists a single database that contains everyone's data. And so this can be hacked, subpoenaed, third-party shared, and so on. Whereas on the other hand, in the local model, all these things are impossible because there is not a single database that exists. Now, if we translate these into the possibilities of these ground truth vulnerabilities, that we can see in the local model, nothing is really possible as a disclosure because there isn't data that can be hacked, subpoenaed, observed, analyzed, used, or shared. On the other hand, under the central model, it does prevent against kind of information leakage via grass charts, models, and so on, but it doesn't protect against all the others. And so importantly, many of these things don't depend on the privacy guarantee coming out of differential privacy. For example, the possibility of a hack doesn't depend on the differential privacy guarantee, but it rather depends on the security of the storage of this organization, and so on. So it's important to kind of realize, although we're seeing different privacy guarantees, really what is typically thought of in the DP space as a difference is this one here, which is whether a kind of analyst looking at your data can see it, or if that will be privatized beforehand. And I have to also mention, this is for a typical implementations, actual specifics can vary. For example, according to some things I've read online, when Uber implemented differential privacy, they used the central model. However, their analysts were not allowed to see the raw data, and this is because they had some concerns about their employees stalking exes and so on. And so privacy was meant to protect against that. And so in that particular implementation, information leakage via the analyst would have been false. But again, this is the kind of typical, when people talk about differential privacy in these models, this is really what they think of. And so then we analyze people's people's like, correctness of their expectations as evaluated against the ground truth in these like two different models. And so importantly, we did not go back and kind of ask like, different survey for the local one versus like central, in part because like virtually all these privacy descriptions apply to both of them. For example, if you talk about like, diminished risk, if you talk about it's a gold standard, if you talk about adding statistical noise, that is true in both models. And so this is how you observe outcomes like this. So we have on top here, we have this like a local model, and on bottom central, and we have like for each of these bars corresponds to kind of one of our like 6 different privacy explanations, as well as no privacy baseline. And so if we look at yes, and then kind of like on this x-axis is the like a fraction of their responses that are correct. When we ask them, do you think a particular privacy disclosure is possible? And they were graded against these like 2 possible rubrics. And so we see here in the central model, people are roughly random guessing. That's the kind of accuracy level we are observing, because these are like true false questions, and the accuracy was like roughly half. On the other hand, in the local model, things are roughly a quarter across kind of like all of these different like privacy descriptions. So this is not good. They're doing like a dramatically worse than like random guessing. And so this really tells us future work is needed here in particular to kind of like tease apart the privacy guarantees of these 2 different models, because like the way things are done in the wild now is not working. And this is of course the goal of like part 2 of this talk. So I will like continue on to part 2. I guess actually I see there's a question. Okay, good. Subtitles, good. Okay. So then I will like continue on to like part 2 of this talk. And this is about how do we communicate some of these like specifics about differential privacy and some of it's like implementation details. And so we really saw the kind of like there is a risk of kind of overstating privacy guarantees. And this depends on kind of 2 core things. And like the first one is this like a deployment model, local versus central. As we saw, although they're very similar and the same definition mathematically applies to them, a lot of the like, practical real world privacy notions in terms of like, who sees our data when are very, very different under these 2. And so now additionally, there's a privacy budget issue that I haven't really spoken about, but in fact is like incredibly important. So we have this like, privacy definition, and we say, as we consider neighboring databases, we're going to have a bound on the ratio parameterized by this bound e to the power epsilon. And the analyst has free choice of this parameter epsilon. And so of course, having a smaller epsilon is going to make this bound tighter, and that's going to give stronger privacy guarantees. And then having a larger epsilon is going to make the bound weaker and is going to loosen privacy constraints. And it's going to therefore give you like a weaker privacy. On the other hand, there is a directly inverse relationship between the epsilon privacy and the accuracy guarantees. And so of course, if I'm giving stronger privacy, then this like constrains my ability to make inferences from the data. And so that's going to give me weaker accuracy. On the other hand, as I weaken that like a privacy constraint, as I turn the knob on the other side, I'm going to get much, much better accuracy. And so this epsilon can range anywhere between 0 to infinity. And you can think of this as kind of like as a kind of like information leakage available quantified in a kind of strange way because it happens to be in this like exponent of a bound on the ratios in the worst case. And what's important here is that one fear is that companies might say, we're using differential privacy, it's the gold standard, you should be really happy with us, be proud, everything is good. And then they can set epsilon really, really large to a point where it's no longer giving meaningful privacy guarantees. And so we don't find a way to really communicate what is the role of this epsilon, that we risk organizations doing that, and then like potentially stating privacy guarantees that are stronger than are real because there is no like standardized language around this. So then we designed like two different studies to address these like issues, and they're both currently in pilots. And so we're very excited. If you have any comments, we're like very open. And so like because of this, I don't have results, but it can show you some of our like survey instruments. So for our first study is going to be about like communicating like a differential privacy models, central versus local. And we thought of like a few different ways you might want to like communicate this. For example, talking about metaphors, saying that like differential privacy makes things like a blurry image or one of those like dot paintings, how it's kind of like blurring out like a specifics of individuals' data, even though the kind of like bigger picture is available. Similar, also talking about like mosaics from a distance, far away, all you see is a global picture, not necessarily like individual tiles. And then we also have some like diagrams and some tables, and these tables are inspired by the kind of work on like privacy nutrition labels. And these are kind of like analogous to food. I don't have to know the entire like chemical process going into making cereal, but there are like a few key facts I have to know that will help me make informed healthy choices, like calories, grams of protein, grams of fat, and so on. And so these are our like privacy diagrams. And so this kind of shows a flow of kind of like your data going through a privacy barrier, indicating there's some kind of additional protection happening. And this is going into a database. And then there are some people who kind of might want to observe it. They can't, it's locked. And then also there's some other like, published reports based on your data, and they also cannot observe it. It is locked. And I want to say this is where kind of I am like really appreciating some of my co-authors with a background in communication, data visualization. We went through many rounds. How do you describe visually like a protected data with the lock, with the blurred picture? Should the eyes be looking down? Should they be looking up? Anyways, there were like many rounds of this, and I'm very grateful for my like co-authors' expertise in this. So on the other hand, we can like contrast this with the central model, where the privacy barrier, rather than being here, has been moved over here. And so this means as your data flows into a database, there are some people who like can observe it directly, and there's some, and then it goes through a privacy barrier, and then there are some people who may want to read like reports, but they can't see it, it is locked. And so we have this one, and then we also have our like privacy tables, and so we go through of these same six groups as like a before, and these are now like a condensed into 5. So we have like a combined here here, kind of like organization and its employees, because we thought there's like not really a big difference between like an organization and the people working at it, because the like organization isn't a person. And so we now have these like five like possible recipients, and they were asking, can they see your data? And we like compare the possibilities under no privacy protection and then with privacy protection. And so, of course, in the local model, things look like this. In the central model, we again see like protections only against like graphs and charts, and we don't provide like protections against these things. And kind of like one thing that we're currently working on is on kind of like alternative versions of this that might make like a central model look less bad, because in this visualization it looks quite weak. But again, it's like, most of these things are not really about the privacy guarantee, but they're about like hackers and kind of like law enforcement, and that isn't really what like a differential privacy like protects against, but it's more about, does there exist a single centralized database? And so then from these, then we asked people as like a comprehension questions, true or false, and we found, and so we asked them basically like exactly this. True or false, an employee working at the nonprofit, including analysts, might be able to like see my exact data, and then we can like compare that against the ground truth. So some preliminary findings that we have is we find that like tables lead to the highest like a comprehension accuracy, and in some sense it's because like the answer is right there. It's a table. Can they see it? Yes, no. However, I feel like as a DP researcher, as I mentioned, some of these tables make the central model look weak in a way that I fear is kind of unfair. And we're exploring how to kind of like indicate this is because of the privacy definition, and this is a thing that is like totally separate. So I'll talk briefly in my last couple of minutes about our like a second study. And this is about like communicating probabilistic privacy guarantees. And this is kind of like in particular about the epsilon value. So we know that we should not tell people epsilon itself, because that isn't particularly informative if you're not used to thinking about math and probabilities and ratio bounds. But instead, we want to kind of think about what are the implications for some things you might be worried about happening based on your data as a function of the epsilon. And so we don't like tell them about the epsilon, but we like compute like a behind the scenes, how likely are some various things to occur under various epsilons, and then we just like present them that. And we also know kind of like empirically, there's like a very large body of work showing that people are like remarkably bad at kind of reasoning about like a private probabilities in the abstract, and it's much more helpful if you're grounded in something, in either a like physical story or something concrete, or a particular randomization device like a die. And so like for that reason, we built up study 2, again, to be kind of like in the form of a like vignette. And we gave them text, but I'll kind of tell you in pictures what is the vignette. So we told them, imagine that kind of like you work on a team of 5 people, and your company wants to like do an employee survey asking if you feel like I'm adequately supported by your manager. And from your lunchtime conversations, all of your other teammates are going to be very like enthusiastically yes about your manager, and your manager knows this, but you are like not really a fan. And so you want to provide feedback that will help your manager improve, but you're really worried about this result getting back to your manager. And in particular, like the company is going to send some kind of report about the total number of like no answers to the manager. And so now we have an opportunity to kind of like inject privacy into this process. And in fact, it matters because of some math behind the scenes, whether that the survey is going to be optional, in which case your choice is to either like participate or to opt out, or if it's mandatory, in which case you can choose to either like respond truthfully or lie. And so then we tell people, again, this is very close to like, vignette 1. So then we tell them to like protect your privacy. Your company will not report exactly how many employees in your team responded no. Instead, they will generate many reports by just adding some kind of random noise in these reports, and they were only going to send one of them to your manager. And again, this is because people are bad about thinking about randomness. And so we say, I'm going to sample a variable from some underlying probability distribution would not work. But if they can like instead imagine, I'm going to generate multiple reports and then pick one, that is a kind of like, randomness reasoning where we see historically better kind of like comprehension of that. And so then we have kind of like a few different like conditions of like how we try to like describe this to the end user. And so one is a verbal condition. In the case where the survey is going to be mandatory, then we tell them verbally, if you respond yes, like this many out of 100 reports will lead your manager to like believe you said no, meaning that you don't feel adequately supported by them, and then like the same thing if you respond no. And so importantly, there kind of like exists an underlying epsilon. We don't tell them, we just tell them this. We do the same thing in the optional condition, and we tell them if you like do or do not participate, this many out of 100 reports will like cause your manager to believe that you responded no. We also have kind of like a few other conditions, including like visualization, showing them visually what does like 39 out of 100 look like. And then we also have a condition where we show them like sample reports sampled from the underlying mechanism with the corresponding epsilon. And so this is the idea, maybe some kind of like vibe check on the number of like outputs they feel good about out of a small handful. And so in this case, we show them lower are some examples of the noisy reports. And we also tell them that the like a total number of no responses may be fractional, or it might be like negative because of this random noise. And so we show them this, and then we ask, do you want to like participate or not in the optional case, or like do you want to be truthful or lie in the mandatory case? And so we also think that it might be a little bit strange for the users to observe -3.2 people said no. And so then we're also going to include a kind of subcondition that includes like a post-processing to kind of make sure that the like results they see are going to be reasonable in some sense. And this is important as a side note. When like a differential privacy was like deployed in the census, they actually had to use a larger epsilon value, meaning lower privacy than they would otherwise, in part because they like felt it was very important to kind of like give people real looking data. And so we are very interested in kind of evaluating whether this difference is important in people's comprehension. And then we ask them, would you participate or be truthful or not, like depending on the case. And then we also are going to ask them if they feel confident, if they feel they have enough information, if they feel, if they understand subjectively, and then a kind of like objective, like a comprehension question. So this is like, ongoing. It's very exciting. And I'll just end by saying, of course, this is a part of a bigger picture. We have like, fantastic, like differential privacy tools in theory, but in practice, they are being deployed, but it's a little bit of a Wild West. And so like the hope of my work in this line is to really improve kind of like formal reasoning about the deployment rollout of these tools. And of course, there exist many other important stakeholders beyond just end users. So I will end there, and we have like plenty of time for some questions. Thank you very much again.
Thanks, Rachel, for the great talk. This is such a new perspective on understanding how humans perceive DP. So if the audience have any questions, please type them in the question answer box. If the panelists have questions, please go ahead and unmute yourself and ask them.
Yeah, thank you for the nice talk, Rachel. I have one question. So it's sort of related to our discussion just before your talk, which is people have been talking about mechanism design. So the idea is that each individual would like to possibly monetize that data in the future. So I have data that could be used for a study and I want to make money off of it. Much of the research in this area sort of seems to assume a model for how users behave. So they assume that now if I give you epsilon I amount of privacy, then there is an assumed linear cost associated with that. I was just wondering if there is a way, since you're doing practical studies on how to convey privacy to users, could you also conduct studies to figure out what is the utility of getting a certain amount of privacy? How do I translate that to money? Because I mean, ultimately, I have to compensate people, right? Nobody's going to give their data for free, but how do I figure out how much to pay to induce them to do this? And typically, people assume a simple linear model for this, partly motivated by Meyerson's work on mechanism design and auction theory and so on. So I was just wondering, in the context of privacy, how can we sort of justify such a model, and if there's a way to sort of do experiments to justify such a model?
Yeah. So I think that is a fantastic question and is really aligned with this work. So we have a couple different answers. I'll say, first of all, in a broader scheme, I think this work is a foundational stone in the building of doing this. So I mentioned before, there's a direct trade-off that is like a quantifiable between the privacy and the accuracy. And so, of course, if you want privacy for the users and you want accuracy of the analyst, well, this is some kind of by criterion objective. And so if you knew how people valued privacy, then you can just plug this in and decide how do you weight analyst utility versus user utility, and then you can solve. But I think, as you mentioned, we don't really have a very good model for how users value privacy as a function of epsilon. And there are a lot of theoretical models assumed because the math is nice, not because there's evidence. And so I think if we can explain privacy to people, if we can explain epsilon, then we can begin to elicit preferences over the epsilon. And so I think these are very much aligned. One a piece of work I have that is in progress. It's a working paper, joint with Katrina Liggett, Ori Chefetz, and Dekel, who are all at like a Hebrew university. So we actually brought users into a lab, and we had them play a game with like a generate embarrassing behavior. Because of course, a challenge is like, how do you bring data into a lab in a way that people feel embarrassed about and is also ethical? That's a real challenge. And so we had them like, play a game in a way where kind of like, if they were more selfish, they would receive higher payments and their partners would receive less. And then we like, announced in the room, a kind of like a differentially private version of like everyone's behavior. And we ran this at like a different epsilon values, and we observed, of course, there was a decreasing utility, or I guess if it's like utility or cost, but it kind of like goes in the direction you would expect as you increase as you increase privacy, people begin to behave more and more selfishly, and you can translate that to how many more dollars did they earn as a result of this change in the epsilon. So I think this is aligned as well. And one challenge is things are very, very context specific. As we observed, people were more willing to share salary data and their health information. And so of course there's not one single utility function over privacy, but in fact it will depend on the context and the use case and the data type and so on.
Thank you. That's very interesting. So this is a working paper?
Yeah.
Okay, great.
Yeah.
I have a somewhat related question. So I think, as you mentioned, explaining the meaning of epsilon to users is quite difficult. So based on those preliminary studies that you showed, what are the main insights? Like, what is the epsilon that the users think is reasonable? And is that in line with what, say, the industry folks are using currently?
Yeah, so we didn't ask about their preferences. I mean, I guess to a certain extent we did. So we asked if they would opt in or opt out. So I don't have real answers I can give yet, because our pilots are very small, and so kind of nothing is statistically significant so far. But I will say there's a real divide in terms of theory and practice. So in theory, people like to use an epsilon smaller than 1. That's kind of considered ideal. And this is in perhaps large part because then you can approximate this term to the power epsilon using a Taylor expansion. You can instead use 1 plus epsilon, and your theorems get a lot easier to prove. And so we have a lot of theorems proved, but the case when it's smaller than 1. But then of course, because of this privacy accuracy trade-off, in practice, companies like to use a bigger epsilon. And so you see things like 1, 2, 4, but still a small constant. There was a period a few years ago where it was alleged that kind of Apple was using epsilon equals 42, and there was a big thing, and there was a Wired article. And so that's the point where it becomes too large and you don't want it. There's really a big gray area. So we know that kind of 1 is good, 42 is bad, and there is a tremendous range in between, and there isn't really standard norms yet. And I think that we should have those. And I think a part of this involves having a better understanding of what people think about epsilons and what makes them feel safe and I'm comfortable, while still acknowledging it should be really context specific, and you're probably going to want different norms. For example, if you're talking about healthcare data versus advertising, it makes sense to have different epsilons, but it's not quite clear what those epsilons are. are yet, but I think this is a very like active and exciting research line.
Thank you. And a related question is, do you also have a idea of doing a study on the delta of the epsilon delta differential privacy? How do you explain delta to users?
Excellent point. I mean, so I think this is interesting, and I would love to see like, how do you explain it? Like, I do think actually here's a case where like, theory and practice really align. They both think that like a delta should be very, very small. Like in theory, it should be like, negligible in the size of your database. And in practice, it's like 10 to the minus 6. And, it's like, depending on the size of your database, those are roughly the same. And so there is much more agreement that it should be very, very small. And delta doesn't have as much of an impact on the accuracy. And so I think that in practice, organizations are happier to have like a small delta because that doesn't impact accuracy as much.
Got it. Yeah, thank you.
Yeah, of course.
We don't have any other questions in the chat. If the audience has any questions, please type them. We are almost out of time. So seems like there are no other questions. Thank you again, Rachel, for an excellent talk.
Of course, thank you. And it was an absolute pleasure being here over Zoom.
Thank you, Rachel.
Yeah,
Thanks.
thank you.